first of all, this project is about the sustainable biomass feedstock supply chains, which is a project which was supported and is by Concawe. And we're working on it, and this project is halfway. But I think it's a great pleasure actually to present the intermediate results of this project now. So very shortly, we'll provide some context of the project itself, an overview of the project, and then also provide some key findings, which we have. This project is midway, but we have some key findings of the first part of this project, and then we provide some conclusion and next steps. With that also, I'd like to shortly introduce the team. We are Ivan and me working on this project, and actually it's a bigger team. We also have a group working in the basement of Utrecht University, and that includes also a master's student, junior researchers, and we have the professor Martin Junger and the associate professor Floor van der Helst working on this project. Shortly, just to provide some context, I think we have also seen already that the introduction of electric vehicles that will provide maybe a decline in the market of biofuels in the road transportation sector. But still, if we could just compare, like this is a publication of recent scenario projections to the future, you can see actually there is a market. There's actually a clear market for liquid fuels in the future. And there's growth, so we can see today's production of advanced biofuels in the European Union. It includes also, this is the combination of Annex A and B, so for around 4 million tons of oil equivalent. And we can see that in most scenarios, there will be an increase of production. And we can see that if we take the large corridor of production, it could increase dramatically. But let's focus on more like the intermediate scenarios. And you can see that actually, yes, production will increase. And if we compare it to today's production of 12 million tons of oil equivalent of all liquid renewable fuels combined, you can see that it might double already by 2030, or at least by 2040, we see an increase to roughly 24 million ton of oil equivalent, but it could also be 12 million ton of oil equivalent, sorry. And by 2050, it becomes more uncertain when we see, indeed, like already presented, this increase in electric vehicles. So a declining market of road transportation fuels might also reduce perhaps the demand for liquid fuels used in transport. And at the same time, we can get this market pull from new sectors also already presented. So we have maritime sectors as well as the aviation sectors that could also revamp this liquid fuel market because there are little options for them to decarbonize. In 2021, Concawe already conducted a very nice study on the biomass supply potentials available for the production of advanced biofuels. And if we do compare these numbers of projections, that we can see that even maybe in the most extreme scenario defined here, it will be okay. There is sufficient biomass available, although we have to say this range is combined with hydrogen. So this is not only biomass, it includes also the hydrogen for processing the fuels into final energy carriers. Nevertheless, the message could be there is sufficient biomass, so this market could actually develop. However, in this project actually we like to start taking that project as a baseline and seeing actually that yes, there might be sufficient biomass available, but this is a complex resource. There are energy crops that need to be developed still. There's hardly any of these lignocellulosic non-food crops on the market today. We have also other waste-based categories that are underutilized, but also meaning since there is no market, they have to still be mobilized. So actually, it really depends on every step and every actor in the supply chain, up until perhaps even end use, what finally the potential will be of these advanced biofuel supply chains. So with the basis of the project of 2021 on the supply potential of biomass, and considering every step in the supply chain, actually we like to assess what could be potentially be available if we consider all these elements together. And given the sake of time, I just presented shortly, but this is the overview of a project what we want to see. Let's just assume a centralized biorefinery, very simple supply chain. This is what's also currently being developed, where you bring the biomass with a truck, like for example straw bales or corn stover, to a biorefinery. You produce it into like final fuel, like ethanol, and then it goes into the downstream logistics of blending, for example. However, it could also develop that we have decentralized production, for example, where you produce an intermediate first, then bringing this more energy dense or better transportable intermediate commodity to a biorefinery, or perhaps maybe even blending it at an actual refinery location before further downstream processing. These are the supply chains we like to assess, and we have this project organized into biomass mapping, so that builds on the existing work by Concawe. On the next slide, we like to see why the locations of these biorefineries are today. Are there any factors why they are chosen for these specific locations? And then finally, we like to combine that. So we combine the locations of biomass supply with biorefinery demand, and then combine into connecting that with the infrastructure available. And the report will be available next year spring. That combines all these steps together. And with that, actually, I'd like to give the floor to Ivan.
Thanks, Rick. Now I'll be showing you the first results we got for the agricultural biomass part. So I'm going to be dividing these results into different key findings that we have come up with, or that our models have actually come up with. And I'm not going to be more in-depth into the methodology. Maybe you can discuss it with me later because it's quite a long methodology. But basically here what you can see is how much biomass is available for these different types. So we have maize stover, cereal straw, lignocellulosic energy crops, and pruning and other crops residues, which we haven't yet mapped to the moment. And here you can see 3 different scenarios depending on different sustainability constraints of different supply constraints. And you can see that it varies from approximately 150 megatons of dry biomass per year in 2030 up to the high scenario, which is more than 200 million tons of dry biomass per year. But what is interesting now is what happened when we try to spatially explicitly try to map these biomass potentials. And here you can see how does it look. You have 3 maps. So the one on the left side of me is the lignocellulosic energy crops. So we took the care of mapping the yield of lignocellulosic energy crops like miscanthus, switchgrass, willow, poplar, these types of energy crops. On the middle, you see the cereal straw, so all the residues that are left after the cereal harvesting, which includes, for example, barley and these other types of cereals. And on the right side, you have the maize stover. And the colors indicate how much ton you can actually have per year, per hectare. And you can see that it goes from a deep green to a light or to a white one, depending on the amount of biomass that you can harvest. And we also included a lot of sustainability criteria. So for example, we also have the sustainability criteria of the RED 2, so you cannot use, let's say, lands that are used for agriculture. We consider also marginal lands. And what we did was we also consider all the, let's say, climatic projections up to 2050 and how these crops' phenological characteristics react to these different climate projections in variables like precipitation, temperature, frost-free days, and all these other variables. And then you can see that there's this is up to 2050, this is the high scenario. So you can see that, for example, there's locations where you can actually obtain high biomass yields, like in some regions of Spain, in some regions of Italy, but in other regions where the climatic conditions are not that adequate, of course, you will be obtaining lower yields. So at the end, where you are producing the yield, or where you are producing these things, so the energy crop will matter a lot. Just to have a note here, we have to enhance the pixels quite some for you to see it. So for example, if Scandinavia part is forest, it doesn't mean that we're using like forest land, it's just because for the audience to be able to see this pixel size. So the first part of the exercise was mapping these biomass potentials. And then what we actually was, let's try to estimate the costs also of the roadside of these different lignocellulosic energy crops and how much it will cost based on the different activities that are required for each crop and for each biomass type. So you can imagine that we consider all the harvesting activities, fertilizers, inputs, diesel costs, labor cost, the cost of renting land. And here you can see there are quite some ranges, what you can see, and basically what we plot here is the average cost for each crop, and the ranges indicate how much is the spatial difference depending of the cost in which location you are actually harvesting this. You can see that it varies up approximately. The lower ones are like, of course, the agricultural residues and other crops like giant reed or willow, because for example, giant reed, you will obtain quite high yields, and then of course if you divide your cost by your yields, and the higher yields you obtain, the lower cost you will obtain, right? So how does that look spatially explicit? I'm going to show you now. So here you see the same maps, same order, and now we are actually checking the cost per ton of of biomass. So again, on the left you have lignocellulosic energy crops, cereal, straw, and maize stover, and we go again from a dark purple to like a lightish purple, and the dark purple is the most, let's say, higher cost. And then you can see there are quite some differences between countries. For example, in Spain, because you have a cheaper cost of land rent or like lower costs of labor, you can actually obtain lower costs per ton of biomass, also because you are actually obtaining higher yields. When you compare it, like for example, the regions of Scandinavia, you will be obtaining low yields but high costs, because like for example, high cost of labor compared to other countries. And then we said, okay, well, this is nice, but what will be one of the main challenges? So because of time, I will briefly go through this. But we also estimated how much water you will actually require to produce these crops in 2050. So basically, what this graph is telling you, it's millimeters per year, but you could also read it as how much cubic meters of water you will require along the whole, let's say, life cycle of that crop until you can harvest it. And I will explain you a bit more in depth about that. And of course, you can imagine that there's quite some specific location variables that determine how much precipitation is available for this water for these crops to actually use water and deliver the estimated biomass potential that we have calculated. And what we tend to see is that where you're obtaining more yields, or like higher yields, like in Spain or Italy, or in other like Mediterranean conditions, you're also quite prone to high water deficit areas. So what happens when we map this? And I also wanted to give you the case of giant reed, because giant reed is one of the crops that actually you can have higher yields, lower costs, but at the end you will be using quite some amount of water. So all the negative values, it means that you're using additional water besides what is available in the form of precipitation. So you need to provide, for example, for giant reed, on average, 1,000 millimeters per year to obtain the achievable yields that we have shown. How does this look spatially explicit? You can see this is only for lignocellulosic energy crops, and everything that goes from yellow to deep red, it's basically you need to provide water for this crop to obtain the expected yields. And then you have the 3 reference times that we assess this, from 2030 up to 2050. And then you can see that also all the high yield areas are also areas where you will be required quite some water. Just to give you an example, the average irrigation water consumption from Spain, so dedicated for agriculture, it's approximately 3,000 cubic meters per year, if you consider only for arable land. And for this part, in some locations, if you translate millimeters years to cubic meters of waters per year, you will be already either double or more. So it will be like either 6,000 to 9,000 cubic meters of water that will be required to achieve these high yields. And now what happens when we actually extrapolate, or like we compare all these challenges, let's say, together. So on the left side, you see again the biomass potential that we estimated for 2050 for lignocellulosic energy crops. On the middle, you see the water balance, or the water deficit. And on the right side, you actually see the aqueduct water index regional water stress. So it basically tells you which areas in 2050 will be already submitted to extremely high water risk based on different activities, in which lignocellulosic energy crops production is not included, for example. And then when you start, let's say, overlapping them all together, you can actually see that most of the high yield areas are actually be located in water-prone risk areas. So therefore, you will need to be asking yourself if it's a good policy to produce these high yield lignocellulosic energy crops when you will be on the other side having a water deficit and you will be having water issues, basically. And then you can see that also from other areas is the opposite. So other areas you will have actually not a high water deficit, but you can actually then produce maybe some crops that will give you like good yields for that area without having a water risk. And
all right, so let's switch again. So I'd like to finalize this presentation with the next step. So we have mapped now the biomass resources and also potential locations of our biomass by refining could develop in the future. So we take that actually as a basis now in the next stage of this project, where we have biomass availability. Only agriculture is presented, but we also have the biomass availability of forest and organic wastes. And we also, with good help of the support of Concawe, with inputs of location factors of where biorefineries might develop, we identified as far as possible these locations where you could, for example, co-locate the plant to generate benefits of synergies, for example. We take that as an additional layer on this model, and finally we connect those with a network model. So it's an ArcGIS-based tool that runs into the transportation of biomass and all infrastructure possibilities together. That needs to be combined with the capital cost and operational cost, and also the options where you can actually produce these fuels together, and we do that within a linear optimization model, which generates lowest cost for an entire system operations of future fuel supply scenarios. But our goal is actually to extract those again and see what kind of strategies are available, and what does it mean in terms of cost of these strategies, but also specifically, for example, in terms of greenhouse gas intensities. Some might not even be feasible if you take the greenhouse gas constraints into account. With that also, I think we have this additional research on biomass supply and advanced biofuel production. We're not going to provide more easy answers, I think, than in the initial study. But I think what we can do is add an additional layer and insights into what it means in terms of how biomass could potentially be cultivated. And actually, what could it mean in terms of smart choices that can be made in the future to develop these advanced biofuels? Because they are essentially for making and meeting actually the climate targets. And actually, every crop and every location in the supply chain actually proves to be relevant. Feedstock supply, intermediate processing, and also final conversion. Secondly, nicely shown also on agricultural biomass, lignin cellulosic energy crops are also seen as kind of a new resource that could reduce, for example, the burden of forestry biomass. But also, there are, again, sustainability considerations like water use. So again, this is not a simple solution that just fits into the system. There are multiple other challenges that link to these energy crops. Finally, and already mentioned, each of the steps in the supply chain, from feedstock production to final conversion and supply to end-use markets, and the prospective locations is important, and we like to consider this in the next stage of this project. Thank you.